In this lesson, we will explore the Pascal's triangle and its application in binomial expansions. The array of numbers shown below is called Pascal's triangle in honor of French mathematician Blaise Pascal. Each row is generated by calculating the sum of pairs of consecutive terms in the previous row. So if we look at row 0, there's just one term. In row 1, we have 1 and 1. The second row, notice we take 1 plus 1, which is 2. The next row, we take 1 plus 2 is 3. 2 plus 1 is 3. So you can see by the arrows that we're the sum of the pairs of the consecutive terms in the previous row is what creates the following row. So let's complete row 7 and row 8 following that same pattern. So we have, first term is always 1. We have 1 plus 6, which would be 7. 6 plus 15, which would be 21. 15 plus 20, which is 35. 20 plus 15, which is 35. 15 plus 6, which is 21. 6 plus 1 is 7. And then we end with a 1. Now looking at row 8, we would do the same thing. 1 plus 7, which is 8. 7 plus 21, which is 28. 21 plus 35, which is 56. 35 plus 35, so taking that sum, which is 70. 35 plus 21, which is 56. 21 plus 7, which is 28. 7 plus 1, which is 8, ending with a 1. So Pascal found many mathematical uses for the array, especially probability theory. We will look how it applies to the binomial expansion. There are patterns in the expansion of a binomial. So if we're given a binomial, a plus b all to the exponent of n, each term in the expansion is a product of a number from the Pascal's triangle, a power of a and a power of b. The coefficients in the expansions correspond to the numbers in the nth row in the Pascal's triangle. In the expansion, the exponents of a start at n and decrease by 1 down to 0, while the exponents of b start at 0 and increase by 1 up to n. In each term, the sum of the exponents a and b is always n, so whatever that exponent is. If the exponent is n, there will be an n plus 1 terms in the expansion. So let's look at an example of the binomial a plus b all to the exponent of 0. In this case, if we did that, it'd be a to the exponent of 0, b to the exponent of 0. Looking at a plus b to the exponent of 1, that means we would have a to the exponent of 1, b to the exponent of 0, and then next term, a would decrease by 1, so a to the exponent of 0, and b would increase by 1, which is b to the exponent of 1. If you look at that term and you add the exponents, in both cases, the exponent being row 1, exponent 1 from the binomial to the exponent of 1, those terms both have a sum of 1, their exponents. Let's follow that pattern for a plus b all to the exponent of 2. So the first term would start at a to the power of n, which is 2. B to the exponent of 0. The second term, then a would decrease by 1, b would increase by 1, a would decrease by 1, b would increase by 1. But in each of those terms, the sum of their exponents is always 2, which reflects the exponent of 2 in the binomial as well as that row number. So looking at that connection. A to the exponent of 3, b to the exponent of 0, a to the exponent of 2, b to the exponent of 1, a to the exponent of 1, b to the exponent of 2, a to the exponent of 0, b to the exponent of 3. In each case, each term, their exponent, sum of their exponents is always 3. Looking at row 4, a to the power of 4, b0, a to the power of 3, b to the power of 1, a to the power of 2, b to the power of 2, a to the power of 1, b to the power of 3, a to the power of 0, b to the power of 4. Likewise, row 5, 5, b to the exponent of 0, a to the power of 4, b to the exponent of 1, a to the power of 3, b to the power of 2, a2, b3. So just following that pattern, as one decreases, the other one increases. Okay, so with that, we're going to now expand in example 2, expand the following. X minus 7 all to the exponent of 7. So looking at the Pascal's triangle, so row 7, okay, those coefficients would be 1, 7, 21, 35, 35, 21, 7, and 1. Okay, so 1, 7, 21, 35, 35, 21, 7, 1. So those are going to be the coefficients of our terms when we expand the following binomial, x minus 7 all to the exponent of 7. So the coefficient for the first term will be 1. The first term is x. It's going to be x to the exponent of 7. And we'd have negative 7 as the second term to the exponent of 0. Then the next term, x to the exponent of 6, the coefficient of 7. And then we'd have negative 7 to the exponent of 1. And we would just continue that pattern. So 21, x to the exponent of 5, negative 7 to the exponent of 2, 35, x to the exponent of 4, negative 3, x to the exponent of 3, negative 7 to the exponent of 4, x to the exponent of 2. Notice the exponents decrease, negative 7 exponents increase, but in total, they're always have an exponent of 1, negative 7 to the exponent of 6, plus 1 to the exponent of 0, negative 7 to the exponent of 7. Okay, we wouldn't leave it like this. We would simplify as far as we can. So looking at each term, always following BADMAS, we deal with exponents first before multiplying with that coefficient. So negative 7 to the exponent of 0 is 1 times 1. So the first term would be x to the exponent of 7. Second term, negative 7 to the exponent of 1 would be negative 7 times positive 7, which would be negative 49, x to the exponent of 6. Next term, negative 7 squared, which is 49, times 21, which would be positive 1029, x to the exponent of 5. The negative 7 to the exponent of 3 would be negative 343 times 35, which would be negative 12,005, x to the exponent of 4. And then we have negative 7 to the exponent of 4, which is positive 2,401 times 35, which would be positive 84,000, x to the exponent of 3. Negative 7 to the exponent of 5, which is 16,807 times 21, which would be negative 352,947 x squared. Negative 7 to the exponent of 6 times 7, which would be positive 823,543x. And then negative 7 to the exponent of 7, which is negative 82,300 and 543. Well, there you have it. Okay, so the Pascal's triangle represents the coefficients in front of your terms. Each term, when we expand that binomial, we start with the first term, decreases in exponents as the other term increases with exponents. Okay, looking at example 3, we're going to expand the following using Pascal's triangle. So we know in A we have x minus 1 all to the exponent of 5. Now, since the exponent is 5, we will look to row 5 at the Pascal's triangle to figure out the coefficients. So we're going to say row 5 would be 1, 5, 10, 10, 5, and 1. And those are going to be the coefficients of the terms in the expanded binomial. So the first term, we have a coefficient of 1. We're going to take x to the exponent of 5, negative 1 to the exponent of 0. So remember, first term's exponent is that n value of 5. The second would be 0. And then the first term decreases by 1, while the second term increases. So second term has a coefficient of 5. So x decreases by 1, increase by 1. Then we have 10 decreased by 1, increase by 1. And in total, the sum of those exponents is always that n value of 5. So 3 plus 2 is 5. So we're on the right track. So 10 x exponent of 2, 5 x exponent of 1 plus 1 x exponent of 0. Once we've done that, we simplify. So negative 1 is 1. So the first term is going to be x to the exponent of 5. Second term, negative 1 to the exponent was negative times 5, so it's going to be negative 5x to the exponent of 4, positive 10x to the exponent of 3, negative 10x squared, positive 5x minus 1. Good. Looking at B, we have 2n minus 0 to the exponent of 4. So row 4 tells us the coefficients are 1, 4, 6, 4, 1. Okay, so starting with the first term, we're going to say 1 is the coefficient. We're going to say 2n to the exponent of 4, and it's going to be negative 3 to the exponent of 0. Next term, coefficient of 4, 2n to the exponent of 3, negative 3 to the exponent of 1. Next term, coefficient of 4, 2n to the exponent of 2, negative 3 to the exponent of 2. Good. Once we've done that, again, using Pascal's triangle, exponent reflects the row that you use. Those are the coefficients. And then we simplify. Always don't forget exponent rule. So that's 2n to the exponent of 4. That means that becomes 2 to the exponent of 4 and to the exponent of 4. Likewise here. Likewise here. Okay, so keep that in mind. So 2 to the exponent of 4, which would be 16, and to the power of 4 times 1, which would be, first term is 16n to the power of 4. Looking at term number 2, 2 to the exponent of 3, 8 times 4 times negative 3, which would be negative 96, n to the exponent of 3. Keep in mind 2 to the exponent of 2, which is 4, times negative 3 squared, which is 9. So 4 times 9 times 6, which would be positive 216n squared. Moving on to the next term, we have negative 3 to the exponent of 3, which would be negative 27 times 2 times 4, which is negative 216n. And then we have negative 3 to the exponent of 4, which is simply positive 81. Okay, moving on to C, we have A plus 4B all to the exponent of 3. So we have row 3, and the coefficients of row 3 are 1, 3, 3, and 1. That means coefficient of 1 for my first term is going to be A to the exponent of 3, and 4B to the exponent of 0. 3, which is A to the exponent of 2, 4B to the exponent of 1. A to the exponent of 1, 4b to the exponent of 2, plus 1, a to the exponent of 0, 4b to the exponent of 3. And then we simplify. The first term we know is going to be a cubed. Okay, second term again using exponent rules, power to power, we have to expand that. So 4 to the exponent of 1 times 3, which would be 12. So we would be at 12 a squared b. Good, keep that in mind. This would be 4 squared, which is 16 times 3, which is 48 ab squared. And then 4 to the exponent of 3, which would be 64 be cubed. Okay, last but not least, we have again, this is row 5. So 1, 5, 10, 10, 5, and 1. My first term we know is 1 coefficient, then we would say 3x to the exponent of 5, negative 2y to the exponent of 0. Second term is 5, so 3x to the exponent of 4, negative 2y to the exponent of 1. Say 3x to the exponent of 3, negative 2y to the exponent of 2, plus 5, 3x to the exponent of 2, negative 2y to the exponent of 3, plus, oops, that was supposed to be 10. Let's change that. Okay. Plus 5, just following the pattern, 3x to the exponent of 1, negative 2y to the exponent of 4, plus 1, 3x to the exponent of 0, negative 2y to the exponent of 5. Okay, and then we simplify. So again, exponent rules, very important because that's where silly mistakes happen. We don't expand properly. So we know 3 to the exponent of 5, which is 243. So the first term is going to be 243 x to the exponent of 5. Okay, because negative, we know the sign's going to be negative. Taking 3 to the exponent of 4, which would be 81, times 5 times negative 2, negative 2, which would be negative 810 x to the exponent of 4, y. Again, silly mistakes happen when we don't expand properly. Okay, 3 to the exponent of 3, which is 27, negative 2 to the exponent of 2, which is 4, so 27 times 4 times 10, which would be 540 x cubed, y squared. Expanding again, 3 to the exponent of 2, which is 9, negative 2 to the exponent of 3, which is negative 8, times 10, which would be negative 720 x squared, y cubed. 3 to the exponent of 1, which is 3, negative 2 to the exponent of 4, times 16 times negative 3 times 5, which would be positive 240 x y to the exponent of 4, and then simplify negative 2 to the exponent of 5, which would be negative 32, negative 32 y to the exponent of 5. Now double check each of the terms. The sum of their exponents should always be 5, and it is.